In this chapter, we'll discuss the alpha substitution reactions on carbonyl compounds. Tautomers are rapidly interconverting constitutional isomers. The best known example is the keto and the eno form of a ketone and aldehyde. Here, an example is shown with a ketone. The keto tautomer is on the left and the eno tautomer is on the right. If we count the number of atoms and the types of atoms in each of these two tautomers, we'll find that they're constitutional isomers of each other. And what makes them different from other constitutional isomers is that these two are rapidly interconverting. In general, the keto form for most carbonyl compounds will be favored. As an example, for cyclohexanone, close to 100% of all molecules will be found in the keto form, and for acetone, even more so. There are a few examples where the eno form is favored over the keto form. This is seen with 1,3-dicarbonyl compounds. For example, if we have a 1,3-diketone as shown here, about 8% of all molecules for this compound would be found in the keto form, and close to or around 92% of all molecules would be found in the eno form. What makes this different from other carbonyl compounds is that the eno form here has conjugation. So this double bond is conjugated to the carbonyl on the left. Conjugation means that we have alternating double, single, and double bonds. That adds extra stability to this particular structure. In addition, we have an internal hydrogen bond, which you can see here between the eno form and the carbonyl form for the other carbonyl. That helps stabilize the structure as well. Another example where we see the eno form being favored is a compound such as a phenol. As we see here, this compound is aromatic, and aromatic compounds have a lot of stability. In fact, they're more stable than your typical conjugated alkenes. We'll learn more about aromatic compounds and aromaticity and how it stabilizes compounds later in the semester. But for now, you can also think of this phenol as being conjugated as well. So that makes this compound, this eno form, more stable. Over 99.9% of all molecules will be found in this eno form. Tautomers can interconvert rapidly under acidic or basic conditions. We'll first look at the mechanism for the acid catalyzed tautomerization of a typical ketone. So starting with a ketone, the carbonyl oxygen will be protonated by an acid, leading to this structure. So this is a protonated ketone, which has another resonance form, which we can draw by taking the electrons in the double bond and sending them to the oxygen. That results in a positive charge. Instead of the oxygen being on the oxygen, it will be on the carbon. Base can then remove the alpha hydrogen and place a double bond between these two carbons. Notice that leads to the eno form of the ketone that we started with. Carbonyl compounds can also tautomerize quickly under basic conditions. Under base catalyzed conditions, a base would remove the alpha hydrogen, which is the most acidic hydrogen on a carbonyl compound, leading to a negative charge in the product of that reaction. So note that what we form is called an enolate. Enolate is the conjugate base of a carbonyl compound. We're going to discuss enolates in detail in this chapter. Enolates have two resonance forms. So if we take this negative charge and move it here, we can put a double bond there. And if we move the pi electrons from the carbonyl to the oxygen, we will have now a single bond there and a negative charge on the oxygen. So these are the two resonance forms of enolates. You can use either one to protonate the enolate and move on. So for example, the oxygen can be protonated by water to produce the enol that is shown here. The enol and keto forms of carbonyl compounds are probably the best known tautomers, but there are other tautomers known. In fact, tautomerization is an important process in understanding the chemistry of DNA bases. We can see on this slide that guanine, for example, has a keto form, which is shown on the left. So it is essentially an amide. And there's also an enol form, which we see here in this structure. There's also a keto and an enol form for thiamine, as shown here. There's an amide shown on the left, and there is an enol form on the right. There's also two different tautomers for adenine and cytosine. So there's an amino form and an imine form, which we see here. Same thing for cytosine, an amino form and an imine form. Before the 1950s, many textbooks would show guanine and thiamine in the less favored enol form. It was a crystallographer Donahue that suggested to James Watson to use the more stable keto form of guanine and thiamine, which later helped them develop the 3D structure of DNA that we know today. So by using the more stable keto form of guanine and adenine, we can draw the base parent that we see on the screen here between guanine and cytosine. So it involves three hydrogen bond interactions. And then using adenine and thiamine in the forms that we see here, we can have two hydrogen bonding interactions as shown. To review tautomerization, let's go over this question where we're going to try to draw the enol form of cyclopentanone. The enol form of cyclopentanone looks as shown here. So we would take one of these alpha hydrogens and remove it, place a double bond as shown here, and then add an OH or a hydrogen to this oxygen of the carbonyl, turning it into a single bond. And so this is the enol form. We could also draw the double bond towards the left. It would give you the same enol in this example, since the ketone we're starting with is symmetrical. Now, the second part of this question asks us to indicate which hydrogens are acidic or most acidic, I guess. So that would involve the four hydrogens that we see here. So that would be the four alpha hydrogens. There's two on this carbon, and there's two on this carbon. The form of a carbonyl compound essentially makes the alpha carbon of a ketone or an aldehyde nucleophilic at that position. We can see this by drawing another resonance form of the enol tautomer. So if we take a lone pair from the OH of the enol and push electrons towards this alpha carbon, we will find this other resonance structure which has a negative charge on that alpha carbon. That means that enols are nucleophilic or electron rich at that carbon, and so they can react with different electrophiles that would add to that carbon. Removing this hydrogen after the addition of an electrophile to the alpha carbon will give you a ketone that has a substituent here. Here is a general mechanism of how ketones and aldehydes will add different electrophiles to the alpha position through the enol form or the enol tautomer. If we start off with a ketone or an aldehyde and we add acid catalyst, the carbonyl will be protonated. So the carbonyl will go after a hydrogen from, let's say, HCl to give us this protonated intermediate. And then this enol would attack an electrophile and do a substitution at the alpha carbon. Note in that process, we are reforming the carbonyl. So we have a protonated carbonyl here plus an electrophile. We can draw another resonance form by breaking the double bond of the carbonyl, pushing electrons towards the oxygen to now have a positive charge on the carbon rather than on the oxygen. And then if base removes this proton, reforms the carbonyl, we will go to a ketone product that has a substituent at the alpha position. So overall, this reaction will replace an alpha hydrogen with an electrophile. So these types of reactions, which we're going to look at in a moment, are called alpha substitution reactions. Note that the first half of this mechanism is just simply an acid-catalyzed conversion of a keto form into an enol, and then that enol will react with an electrophile to add a substituent at the alpha position of the carbonyl. Aldehydes and ketones will react with Cl2, Br2, or I2 under acidic conditions to replace a alpha hydrogen with a halogen. As an example, acetophenone, when mixed with acetic acid, which would be our acid catalyst, and one equivalent of Br2, will lead to replacing one of these three alpha hydrogens with a bromine. Note that the left side has no alpha hydrogens, and so no substitution will occur on that side. If we have an unsymmetrical ketone, the alpha halogenation can occur at one of two locations, and generally, we will get the substitution at the more substituted side of the ketone, since that is where the more substituted enol will form, and more substituted enols are generally more stable than less substituted enols. This is similar to what we see with alkenes. So you can think of an enol similar to an alkene. And so using this example here, we have this unsymmetrical ketone. It will prefer to form an enol on the left side of the molecule. So here is the enol form that would form. We would find a double bond on the left side. We would find an OH here where the carbonyl used to be. And we'll have a methyl group here as well. So the molecule prefers to form this enol rather than the less substituted enol, which would look something like this. So same cyclopentane. The double bond of the enol would be towards the right side in the less substituted enol. We still have the methyl group here. So this enol is less favored since the double bond is less substituted compared to the double bond on this one. And so the reaction will occur through the more substituted enol, and therefore the substitution of the halogen will occur on the left side of this ketone. So look at the acid-catalyzed alpha halogenation of ketones and aldehydes. It starts off with a ketone or an aldehyde being protonated by acid, either acetic acid or HBr, which results from the mixing of acetic acid and bromine. The carbonyl gets protonated. That gives us this protonated carbonyl, which then reacts with base. The base will remove the acidic alpha hydrogen, form a double bond here, and then break the carbonyl. That leads us to this enol. Notice that these first two steps are essentially the conversion of a keto tautomer into an enol tautomer. The enol tautomer will then react with Br2, where a substitution occurs now at the alpha carbon. We can draw two resonance forms of this intermediate. So if we break the carbonyl, we can place a positive charge on the carbon rather than on oxygen. Base will then remove the proton on this oxygen, and we can also use the same base to remove the proton on this other resonance form. Either way, we're going to go to a product that has a carbonyl, and we have replaced one of the alpha hydrogens with a halogen. Treating alpha haloketones with base yields an alpha beta unsaturated ketone. An example shown here with an aldehyde. If we do an alpha halogenation under acidic conditions, it produces the typical alpha halogenated product, which if we add pyridine and generally we heat it, we can do an elimination reaction by removing this proton, leading to a double bond here and elimination of the halogen. As a result, we get an alpha beta unsaturated aldehyde. Note that this is called an alpha beta unsaturated aldehyde since the alpha carbon and the beta carbon contain a double bond. In the next example, we have a ketone that is unsymmetrical. If we add Br2 in acetic acid, we can do an alpha halogenation of the more substituted carbon. And so we get a bromine on this carbon. Treatment with pyridine and heating leads to a elimination reaction that produces an alpha beta unsaturated ketone. Let's now review the reactions from this section by doing this problem. We want to prepare a 1-pentene 3-one compound from 3-pentanone. 1-pentene 3-one from 3-pentanone, we would do an alpha halogenation under acidic conditions. So we could add one equivalent of Br2 and acetic acid to replace one of the alpha hydrogens with bromine, and then treatment of this product with pyridine and heating will result in an elimination reaction that leads to a double bond between the alpha carbon and the beta carbon as seen in 1-pentene 3-one. Carbonyl compounds like aldehydes and ketones are considered weak acids that can be deprotonated with strong base, such as lithium diisopropylamide or LDA. As shown in this example, if we have a ketone and we add base, we can remove an alpha hydrogen. That leads to a negative charge on this carbon, producing an enolate. Enolates are the conjugate base of a ketone, an aldehyde, or other carbonyl compounds. Note that enolates always have two resonance forms, so we can put a negative charge on the alpha carbon from the carbon that we removed the hydrogen, or we can move that negative charge towards this oxygen of the carbonyl. So if we move this negative charge in this direction and break the double bond, we can create the other resonance form that you see here. Note that in going from a ketone to an enolate, we're rehybridizing the alpha carbon from sp3 hybridized to sp2. And that is true in both resonance forms. LDA, which is a base we're going to become familiar with in the next few slides, is a common base that we use to deprotonate ketones and aldehydes. It stands for lithium diisopropylamide, so a nitrogen that has a negative charge and it has a couple of isopropyl groups. When it comes to bases, the first base that probably comes to mind is sodium hydroxide. However, sodium hydroxide is not a good enough base to deprotonate most ketones. We can determine that based on the pK of the conjugate acid, which is water, which has a pK of almost 16. Based on this pK value, we can determine that less than 1% of all ketone molecules will be converted into an enolate. Sodium ethoxide has a conjugate acid of ethanol, which has a pK of about 16 roughly. Very similar to the pK of water, and just like water and its pK, we can determine that sodium ethoxide is not a strong enough base to deprotonate most ketones, at least effectively. Less than 1% of most ketones will be converted into an enolate form. Compare that to LDA. LDA is a very strong base. Its conjugate acid is this amine shown here, which has a pK of about 36. Based on that pK value, we can determine that LDA will deprotonate a typical ketone 100% into its enolate form. As a result, typically we use LDA very often to deprotonate not only ketones but also aldehydes and many other carbonyl compounds. LDA has two isopropyl groups which prevent LDA from acting as a nucleophile, so it only functions as a base. Sodium hydroxide and sodium ethoxide, although they're not the most effective bases to deprotonate ketones and other carbonyls into enolates, they can still be used in certain cases, as we'll see in this chapter. This table has a number of carbonyl compounds as well as carbonyl-like compounds that can be converted into an enolate or something similar to an enolate by treatment with base. Carboxylic acids have a pK of about 5, and that pK value refers to the hydrogen on the oxygen. So when a carboxylic acid is treated with base, typically it is that hydrogen that is deprotonated first. This methyl nitro compound, when treated with base, can also be converted into a compound that is similar to an enolate. So one of these alpha hydrogens will be removed. It has a pK of about 10, which is a very acidic hydrogen. A primary amide or even a secondary amide, which both contain a hydrogen on a nitrogen. Similar to a carboxylic acid, the most acidic hydrogen, it is the one attached to the nitrogen. It has a pK of roughly about 15. The rest of these carbonyl compounds will be converted into an enolate when treated with a strong enough base such as LDA. For example, an aldehyde has a pK of about 17, and that refers to the alpha hydrogens highlighted here. Ketones typically have a pK of roughly about 19, and so they are converted into enolates when treated with base. An ester has a slightly higher pK of about 25. Nitriles, again, they don't quite look like a carbonyl compound, but they behave when treated with base similar to other carbonyls. And so the pK of a typical nitrile is about 25 as well. An amide, at least those that are tertiary, can be converted into an enolate when treated with base. The pK of the alpha hydrogens on an amide, it's about 30. Notice that starting with this aldehyde here and going down to the amide, the pK values are increasing and is sort of a correlate. There is a correlation between the stability of the carbonyl and the pK value. So typically the least stable or the easier to break double bond of the carbonyl, the lower the pK value. And one way of rationalizing this is with amides, you have a very stable carbonyl, and so it is much harder to deprotonate one of these alpha hydrogens, which would result in sort of getting rid of part of the double bond character between the carbon and oxygen once you convert it into an enolate. 1,3-dicarbonyl compounds such as 2,4-pentane dione have an extremely acidic hydrogen in between the two carbonyls. So as shown in this example, these two alpha hydrogens have a pK of about 9. Compare that to a typical ketone, which has a pK of about 19. The reason why these hydrogens are more acidic than a typical hydrogen, alpha hydrogen on a ketone is because removal of one of these hydrogens produces an enolate that is stabilized by several resonance forms. So when we remove one of these hydrogens, we get this enolate, which can be exchanged into two other resonance forms by moving this lone pair towards one carbonyl. For example, the carbonyl on the left will lead to this resonance form. Or if we move the electron densities in the other direction, we can form this other enolate with the carbonyl on the right being having a negative charge on it. Other 1,3-dicarbonyl compounds will also be very acidic, much more than a typical carbonyl compound. So for example, if we have a ketone and an ester near each other, so 1,3 to each other, the pK is roughly about 11. When you have two esters, the pK is about 13. Note that a single ester would lead to a pK of an alpha hydrogen of being roughly about 25. A nitro compound and an ester lead to a pK value for these alpha hydrogens of about 6. And then a nitrile and an ester lead to the alpha hydrogens here in between the two functional groups having a pK of about 9. In this question, we want to identify the most acidic hydrogen in each of the following compounds. And then after, we want to rank the 3 compounds shown here in order of increasing acidity. When it comes to carbonyl compounds, generally the most acidic hydrogens are those that are at the alpha carbon of a carbonyl. In the cases of 1,3-dicarbonyl compounds, the alpha hydrogens in the middle, in between the two carbonyls, are the most acidic. So in this example, we have two types of alpha hydrogens. We have those shown in green and the ones shown here in the center. The ones in the center are more acidic than the ones on the right side. Since these two hydrogens are in a carbon that is in the alpha position of two carbonyls. With the next example, we have only one type of alpha hydrogen, which is the one highlighted here. So on an ester, the CH3 hydrogens are generally not that acidic. Neither are the hydrogens on the beta carbons, which would be these two methyl groups. In compound C, we have one type of alpha hydrogen, which is the one highlighted here in color. The hydrogen directly attached to the carbonyl of an aldehyde is not generally acidic. Between these three types of alpha hydrogens or hydrogens on these carbonyl compounds, the most acidic ones would be the ones found in a 1,3-diketone. So that would be the most acidic, followed by this compound here. So this is an aldehyde. pK of an alpha hydrogen on an aldehyde is generally about 17. A typical ketone is about 19. An ester is a little bit less acidic. So this is about maybe 25 or so. So B is the least acidic. You don't have to memorize pK values. Those will be generally provided to you if you needed them. But one way of sort of remembering or figuring out which of these compounds is most acidic Usually 1,3-dicarbonyls will be most acidic. In between typical carbonyl compounds, the more electrophilic a carbonyl is, generally the more acidic the hydrogens are. So aldehydes are generally the most electrophilic among most carbonyls. So that would be the most acidic type of hydrogen, followed by ketones, followed by esters, followed by amides. Enolates are by nature nucleophilic, and they react with electrophiles in one of two ways. They can either add an electrophile to the oxygen, as shown on this center mechanism. So the oxygen would attack an electrophile and then attach to it, essentially trapping the enol. This happens often with silicon protecting groups, which prefer to add to the oxygen since they form a very strong bond. Some electrophiles, I would say most electrophiles, generally add to the carbon of an enolate. So this alpha carbon in one of the resonance forms of enolate has a negative charge. And so that carbon can react with an electrophile to attach at that position. This generally happens in alkylation reactions and halogenation reactions. Enolates are great nucleophiles and they can react with a number of electrophiles. One of those are halogens. So if a ketone or an aldehyde is converted into an enolate under basic conditions, we can do an alpha halogenation. Here's an example. We have a ketone that has an alpha hydrogen. If we add an excess of sodium hydroxide, one of these alpha hydrogens will be removed by base to form an enolate, as shown here. And then that enolate will react with the chlorine. So we're using chlorine as a second reagent. That chlorine will add or substitute at the alpha position. So essentially, we're replacing an alpha hydrogen with an alpha chlorine. Now, this product here with the chlorine is actually more acidic than the original ketone because of the electron withdrawing group, which we just added, the chlorine. And so the next alpha hydrogen, which is this one here, can also be replaced by a chlorine. And then we can repeat that again on the left side. So there are two alpha hydrogens here that would also be replaced. Since as we continue to add chlorines, we're going to make the ketone even more acidic and therefore more willing to react in this reaction. So for that reason, it's very difficult to just simply replace one alpha hydrogen with a halogen. We usually replace all of the alpha hydrogens with halogens. So we generally use an excess of base, an excess of the halogen, whether it's chlorine or bromine, to get a product that has all of the alpha hydrogens replaced by halogens. Note that this is different from the acid catalyzed alpha halogenation, which generally we can control and we could do a single substitution. In the base promoted reaction, we have to use an excess of base, an excess of electrophile to replace all of the alpha hydrogens. This reaction works great with Br2 and I2 as well. The haloform reaction is a spin-off of base-promoted alpha halogenation. This reaction occurs specifically when we're using a methyl ketone, as shown by this example. When we have a methyl ketone, initially, when we're using an excess of base and an excess of a halogen, we're going to replace all of the alpha hydrogens with halogens. That would also occur on the left side of this ketone if there were alpha hydrogens. In this example, there's 3 methyl groups, so there are not any alpha hydrogens to replace. So only the 3 hydrogens on the right side will be replaced by halogens. From there, we have now a compound that is very electrophilic. Those 3 halogens will make this carbonyl very electrophilic, and an acyl substitution occurs where the OH will replace the carbon, which has the 3 halogens on it, and we end up with a product that has um, is either shown as the conjugate base of a carboxylic acid or more traditionally is shown as a carboxylic acid. The byproduct of this reaction would be iodoform if we're using I2. Note that iodoform is a brightly yellow solid, and so this is a reaction that we'll talk about in a moment that sometimes is used to test whether you have a ketone that is a methyl ketone. Let's look now at the mechanism for this reaction. So if we start off with a methyl ketone and we add an excess of base, an excess of a dihalide like Cl2, Br2, or I2, we will initially replace all three alpha hydrogens on this methyl group with halogens. That CX3 group will now make this carbonyl very electrophilic, and an OH from sodium hydroxide will attack that carbon, break the double bond to put a negative charge on this oxygen. That gives us this tetrahedral intermediate, and then we do an acyl substitution where the carbonyl reforms and we eliminate this CX3 group. And so there is sort of a turning point in the base promoted alpha halogenation that when we have a methyl group, we end up with these three halogens, and that sort of turns this reaction from a typical alpha halogenation reaction into what we call the haloform reaction. So when we eliminate this leaving group, we end up with a carboxylic acid. Now, because this reaction is done under basic conditions, this carboxylic acid will be deprotonated and we get the conjugate base of a carboxylic acid. So that's what we see here as a product, but occasionally you might see a second step where we add aqueous acid, which will get rid of the base and also protonate the conjugate base of the carboxylic acid. So you might see the product of the haloform reaction shown as a carboxylic acid. The haloform reaction, specifically when we use I2 as our halogen, it is sometimes used to detect whether we have a methyl ketone in an unknown, perhaps, or a product from a reaction. And so the reason for that is the iodoform byproduct is a yellow solid, and so you'll get this yellow precipitate in the reaction when you have a methyl ketone. Here's another example of the haloform reaction. So using an excess of sodium hydroxide, an excess of Cl2 with this methyl ketone, followed by aqueous acid, we can get or turn that methyl ketone into a carboxylic acid. So notice we're replacing the methyl group with an OH group. This happens because these alpha hydrogens are initially replaced by Cl chlorines, and then sodium hydroxide, or the OH specifically, will do an acyl substitution with this carbonyl to replace the leaving group here, and we end up with the carboxylic acid. The byproduct of this reaction will be chloroform. Here's another example. This time, we don't have a methyl ketone. We have instead an ethyl group, and so the alpha hydrogens, these two here, will be replaced by bromine, and so we get this just the plain old boring base promoted alpha halogenation reaction. Notice on the left side there is no alpha hydrogens, so nothing happens on that side. An important reaction of enolates is an alkylation reaction. So if we start off with a ketone or any other carbonyl, and we add a base such as LDA, we form an enolate. And then if we add an alkylating agent such as an alkyl tosylate, we would add an alkyl group at the alpha position. So in this example, we have an ethyl group here, so we're going to add an ethyl group coming off of this methyl carbon. So the product has the methyl carbon that initially was there in the reactant plus an ethyl group. Note that on the left side, there is no alpha hydrogen, so there is no chance to do an alkylation on that side of the molecule. Here's a general example for the mechanism. So if we start off with a ketone and we add base, such as LDA, the base would remove this alpha hydrogen, adding a negative charge on that carbon. And so notice we have produced an enolate. So the enolate is the conjugate base of a ketone or some other carbonyl. That enolate will then do an SN2 reaction on an alkylating agent such as an alkyl halide or an alkyl tosylate. Since this is an SN2 reaction, this is better when it's a methyl group here or a primary alkyl halide or alkyl tosylate. The alkylation reaction can occur on a number of carbonyl compounds. For example, an ester, when treated with base and methyl bromide, would lead to a methylation at the alpha carbon. Note that for esters, that is the most acidic hydrogen, so that's where the reaction occurs. With a nitrile, we get a similar reaction. So nitriles, again, are lumped in with carbonyls because they do similar reactions. So we can add base to remove the alpha hydrogen, and then an alkylating agent such as this guy here is a methyl chloride, not a methyl chloride, but a primary alkyl chloride that would lead to an alkylation at that carbon. So note that we have a CH2 followed by a carbon with a double bond, and that's what we see in the product. We have a CH2 and then a double bond after. With a cyclic ester known as a lactone, if we add LDA, and we can form the enolate, and then we can methylate it with methyl iodide, and so you see that methyl group in the product. As long as our carbonyl compound contains alpha hydrogens, we can do multiple alkylation reactions as illustrated on this slide. So here we have a 1,3-diester. If we add base, we can remove one of these alpha hydrogens, form an enolate, and then that enolate can react with an alkylating agent to add an alkyl group. We can repeat this again since this particular compound has another alpha hydrogen in between these two esters. So if we add base, we can add or make an enolate again, which can react with a second alkylating agent, which doesn't necessarily have to be the same as the first one, and add a second alkyl group. Note in this example, we're using a diester, and notice the base that we're using. So this is typical when we're using a base such as this. We generally will either use LDA, which is a base that is not nucleophilic, or if we're going to use something like a koxide base, we typically use the base that would or would not lead to a substitution reaction on the ester. So we used basically the leaving group on the ester just in case this reaction or this base decides to do an acyl substitution, we're going to end up with the same ester. When dealing with a ketone or a diketone that has multiple alpha hydrogens, we have to worry about enolate regional selectivity. So meaning, where is the enolate going to form when we have multiple alpha hydrogens? So if we add LDA to this 1,3-diketone, LDA will remove one of these hydrogens in the center since those are the most acidic, and the ethyl group from ethyl bromide would then transfer to that carbon. So for that reason, we get this product. We can repeat another alkylation reaction by adding LDA, which will remove another alpha hydrogen from the center carbon, and then the methyl group from methyl bromide would transfer there. At this point, if we add base and methyl tosylate, we can add a methyl group to either the carbon here or the carbon here. It would not matter because of the symmetry of the molecule. So we would get a product that you see here. If we were to add LDA and another alkylating agent, the next reaction would occur on this carbon, as we'll talk about soon. LDA prefers to go after the least substituted carbon when you have a compound like this, so the alkylation would occur there. If we add LDA again, we're going to be dealing with a symmetrical compound at that point, assuming we added a methyl group on this side. So the alkylation would occur equally on the left side or the right side. When we're dealing with unsymmetrical ketones such as this, when we're working with enolates, we have to worry about whether the enolate will form on the more substituted side or the less substituted side of the ketone. Generally, with LDA at very low temperatures, we usually form an enolate on the less substituted side of a ketone. This is referred to as the kinetic enolate. So that would be the enolate that forms by removing one of the hydrogens, either one of these, on the left side of this ketone, which is the less substituted hydrogens. The reason we refer to that as the kinetic enolate is because that is the enolate that forms the fastest under these conditions. So LDA is a base that is a very strong base. It's also a very bulky base. So it prefers to go after the least substituted hydrogens rather than this hydrogen here, which has a methyl group sort of blocking partially the hydrogen. At lower temperatures, this is sort of enhanced. This effect is enhanced. And so LDA will preferentially remove one of the less substituted hydrogens more than if it was at higher temperatures. As a result of formation of this kinetic enolate, the alkylation occurs on that side. And so the product is referred to as the kinetic product or the kinetic alkylation product. Okay, so when we hear the term kinetic product, kinetic intermediate, that refers to the fact that that intermediate or product is the one that forms the fastest. Note that we can do a alpha halogenation with LDA as a base. So this is simply a base promoted alpha halogenation, similar to what we saw with sodium hydroxide. That typically, when we're using LDA at low temperatures, will lead to the kinetic enolate. So for this ketone, that would be forming an enolate on this carbon rather than this one. And so the halogenation would occur on that carbon. And so for that reason, we get this kinetic product here. Kinetic intermediates and kinetic products are typically formed from conditions that are non-reversible. They're usually involve non-protic solvents when we're dealing with bases. So if we're using a base as one of the reagents to form, let's say, a conjugate base like an enolate, by using non-protic solvents, we prevent the reaction from being reversible. Doing it at low temperatures also enhances the percentage of the kinetic intermediate and also the kinetic product. And also the fact that we're using a bulky base like LDA here also helps form the kinetic enolate and eventually kinetic product. Symmetrical ketones such as this, we can also form the thermodynamic intermediate or the thermodynamic enolate. And so that typically is done with a base such as sodium hydroxide mixed in with a protic solvent like water, which would allow an equilibrium to occur between this base, removing the more substituted hydrogen as well as the least substituted hydrogens. And so those reactions happen reversibly. So the base removes the hydrogen, then the water puts it back on, and this process goes back and forth, removing both the hydrogen on the right side and the left side and putting them back on. And eventually we're going to get to an equilibrium where we have a percentage of the kinetic and the thermodynamic enolate as well as the ketone. And for the most part, when we're doing a reaction on the thermodynamic conditions, meaning reversible conditions, the most stable intermediate, in this case the enolate, would be the one that is form in the highest percentage. So when it comes to enolates, having a more substituted enolate is favored. So one way of thinking about it is if we have an enolate, and I'm going to redraw the starting ketone here. If we have our ketone, one of the resonance forms for the ketone or the enolate of the ketone would be having a double bond here next to this methyl group. Compare that to the other possible enolate, which would be this one here. And the methyl group is on this side, and the double bond of the enolate would be this way. So these are the two possible enolates you can get from this reaction. The one on the top is called the thermodynamic enolate, which basically forms by removing this hydrogen. And this is the kinetic enolate, which we from removing one of these hydrogens. On the thermodynamic conditions, aka reversible conditions, this is the more favored enolate because we have a double bond that's more substituted. And so on the reversible conditions, we get this enolate preferentially, and so the alkylation occurs on that carbon. Okay. We can do an thermodynamic halogenation. This is what we saw under the acid catalyzed alpha halogenation that we saw earlier. You might remember that that halogenation occurs typically on the more substituted carbon, although technically that was going through an enol, not an enolate. It formed the thermodynamic enol, which led to this thermodynamic halogenation product. So in conclusion, kinetic conditions means we're using irreversible conditions, typically non-protic solvents if we're involving enolates. LDA is great for it because it's a bulky base. Low temperatures is also helpful. For the thermodynamic enolate, we want to form it under reversible conditions, which means using a protic solvent, using a base such as sodium hydroxide, which is not the greatest base. It kind of slowly removes the proton, and so water can add it back on and so forth. Alkylation reactions of the alpha carbon of a carbonyl occurs in many syntheses and also in many biosyntheses. So here's an example of the biosynthesis of this antibiotic shown here, which is formed partially through an alkylation reaction. So base removes this alpha hydrogen, and we have a carbonyl here. Makes those hydrogens acidic, and so base can remove it. It forms an enolate, and so we have that here. Although this is actually shown as an enol, which is essentially the same thing. We're removing this alpha proton, and then the carbonyl is getting protonated. So we have an enol, which is also nucleophilic at the alpha carbon, similar to enolates. In the next step, base will remove this proton, and this alpha carbon will go after the methyl group of a molecule we've seen before called SAM. SAM is a great alkylating agent, specifically is great at transferring a methyl group. And so the alpha carbon goes after this methyl group, eliminates the rest of the molecule. Think of the rest of the molecule as a leaving group. And so we added this methyl group, which eventually ends up on the final antibiotic. Note that this reaction is stereoselective, so the methyl group adds from one side of this double bond here, and this is possible because we're dealing in a biological system with enzymes that have chirality to them, and then can add the methyl group only on one side of the double bond as opposed to where this hydrogen is. This can not happen in a lab. Unless we throw some sort of chiral reagent into the reaction that would selectively add the methyl group on one side. All right, so to review the reactions of enolates, let's attempt this problem. So how would we potentially make this product here? So this is ethyl 1-methyl cyclohexane carboxylate, and notice it has a methyl group on this carbon next to an ester. So looking at the compound that we want to synthesize, which is this compound shown here, one way to do an alkylation reaction on this ester is to add this methyl group, which we can do by adding LDA followed by methyl iodide or methyl bromide to add the methyl group from this initial ester. Another reaction of enolates is the silation reaction, where we can convert a ketone or an aldehyde into what we call a silo-enol ether, which is essentially a protecting group for ketones and aldehydes. This is how this protecting group can be added. So if we start off with a ketone, if we add LDA at -78, which would form the kinetic enolate. So in this unsymmetrical ketone, that would mean removing this alpha hydrogen here as opposed to the one on this carbon. So LDA will remove that hydrogen, form the kinetic enolate. And then if we add TMS chloride, which is this compound here, trimethyl silochloride, the oxygen would attack the silicon, eliminate the chlorine through an SN2 reaction essentially to add the TMS protecting group on the oxygen. Note that oxygen has a strong preference for forming a bond to silicon rather than carbon to silicon. So the oxygen to silicon bond is a stronger bond. So generally we end up with the silicon on the oxygen. Notice that the product here essentially is a trapped enolate, and that's going to play a role later on in some of the reactions we can do with this compound. There are two resonance forms of enolates, as we have mentioned before, and I'm showing here one of them for this kinetic enolate, but there's another one where there's a negative charge on the carbon. Some of the electrophiles we cover in this section, like alkylating agents and halogens, they generally add to the carbon. But as we see with this example, silicon will generally add to the oxygen. So we prefer to use this resonance form for this reaction. Once we have the silicon protecting group on an enolate of a ketone or an aldehyde, we can remove it if we wanted to by using TBAF. So TBAF is tetrabutyl ammonium fluoride. The only thing you need to remember about TBAF is that it's a fluoride source. The F- is a good nucleophile that would add to silicon and eliminate the oxygen, essentially releasing the enolate that was trapped in that protecting group. The driving force behind this step is the fact that fluorine forms an even stronger bond to silicon than oxygen to silicon. Once you have an enolate release, you can do one of two things in general. One of the reactions that you can do is add acid, which would turn this enolate into the original ketone where it came from. We'll see that on the next slide. A more sort of useful reaction is we can use this enolate that was just released to do an additional reaction and specifically add an electrophile to the alpha carbon. So if we add an alkylating agent like this ethyl iodide, we can add an ethyl group at that position. So in this reaction, we're essentially doing two reactions in one. We're removing the protecting group and then doing an alkylation reaction on the alpha carbon. If we simply want to return or get back to the original ketone where this silo-protected enolate came from, we can, instead of using an alkylating agent as a second step, we can use aqueous acid. So TBAF would initially remove the protecting group, give us an enolate, and then if we add aqueous acid, that enolate would react with it to form the original ketone where this trapped enolate came from. Very interesting reaction is the decarboxylation reaction of beta-carbonyl carboxylic acids. Here's an example if we start off with a ketone that is in the beta position of an ester, we can do one of these decarboxylation reactions. As a reminder, when you have an ester, the first carbon is called the alpha carbon. The next carbon is the beta carbon. And so we can call this a beta ketoester. These types of compounds, when you treat them with acid, so sulfuric acid, for example, and water, and heat it, the first thing that's going to occur is we're going to hydrolyze this ester into a carboxylic acid. So this is a reaction that we saw in the carboxylic acid chapter when we looked at acyl substitution reactions. And once you have a carboxylic acid that has a ketone or any other carbonyl at the beta position, a decarboxylation reaction will occur very readily. So this carboxylic acid, one way of looking at it, if we turn it, will look like this, facing towards the ketone. The ketone can be protonated by the carboxylic acid. That will lead to the bond between the OH group. Those electrons go in here, forming a double bond. And then this bond breaking to form a double bond here. The result of those electron movements would be an enol from the left side of this molecule. So we have a double bond, and we are turning this carbonyl into an OH. So that's our enol. And then from the right side, this becomes a CO2 molecule. So this carbon is double bonded to this oxygen, as well as double bonded now to this oxygen. So you have now CO2. So we have essentially removed this carboxylic acid from the right side of the ketone. The enol, as you might recall, is a tautomer of ketones. And so anytime in a mechanism you have an enol intermediate, it would be converted into the corresponding carbonyl, in this case, this ketone here. And so from this reaction, we have turned this beta ketoester into a ketone, and we have sort of eliminated this entire ester, since we first turn it into a carboxylic acid, and then it is decarboxylated as CO2. Note that this reaction can occur with any carboxylic acid that has a beta carbonyl. So we could have an aldehyde here, we could have another carboxylic acid, we could have an ester, or any other carbonyl. A few more examples of decarboxylation reactions. This first example, a general example of a diester that is 1,3 to each other. If we heat it up with aqueous acid, so that would be a mixture between sulfuric acid and water, for example, the first thing that would happen is these two esters would be hydrolyzed into carboxylic acids. And since they are 1,3 to each other, one of these carboxylic acids would be decarboxylated. So we can, let's say, keep this carboxylic acid and eliminate this one. And so you'll end up with this product here. We'll also have CO2 and ethanol as byproducts. Ethanol came from the hydrolysis reaction, so the leaving groups on the esters become ethanol molecules. Here's a look at how this reaction occurs. So this is a 1,3 diester, dicarboxylic acid. So that would be the intermediate of this reaction after you hydrolyze the two esters. One of the carboxylic acids would be like this. The other one turns towards it so that the carbonyl can be protonated. We can reform a double bond here, break this carbon-carbon bond, form a double bond here, and the result of that would be, from the right side, an enol of a carboxylic acid. So we have a double bond and then an OH here. So that's an enol of a carboxylic acid. That's what we see here. The left side becomes a CO2 molecule, so we're forming a double bond here between the carbon and oxygen. We already have a carbon-oxygen double bond, so we end up with a CO2 molecule. The enol of the carboxylic acid, similar to the enol of a ketone, is going to be converted into the carbonyl form. So in this example, this enol becomes a carboxylic acid. In this next example, we have carbonyl that is beta to a carboxylic acid. In general, any carbonyl will lead to a decarboxylation reaction, forming an enol initially, and then that enol becomes a ketone. The malonic ester synthesis is a synthetic strategy that sometimes we use, combining two reactions we've seen in this chapter, which is the alkylation of enolates followed by decarboxylation to make a carboxylic acid that is exactly 2 carbons longer than the alkyl halide we're using. Now, you don't have to memorize this strategy per se. Just be more familiar with the two reactions involved, which we have covered in this chapter, and then using them for a synthesis. Here's an example. If we have 1-bromobutane and we take a malonic ester, and it doesn't matter which ester we use, and we add a base such as sodium methoxide. The base would deprotonate one of these alpha hydrogens, which will lead to an alkylation of that alpha carbon. And then if we use a decarboxylation, so adding aqueous acid and heating the ester, or the diester in this case, will lead to first hydrolyzing the two esters into carboxylic acids, and one of those two esters would be removed by decarboxylation, leading to a carboxylic acid that is 2 carbons longer than the original alkyl halide. So what we did here is, imagine we remove this ester entirely through decarboxylation. The other ester becomes a carboxylic acid. It involves 2 carbons, so we have 1 carbon here, 1 carbon there that was added to the alkyl halide that we started with. Now, we don't necessarily have to stop after one alkylation. We can do a second alkylation. Let's say remove this hydrogen with base, and we could add a methyl group in this example. And then if we do a decarboxylation, we'll once again remove one of the two esters, and the other one is converted into a carboxylic acid. We can add rings like a cyclopentane or a cyclohexane ring to the alpha carbon of a carbonyl compound or a dicarbonyl compound. So using malonic ester as an example and adding base to it, we can make an enolate, which is already shown here. That enolate would react with a dialkyl halide. First it would react with one of the carbons with the leaving group and add this carbon chain to it. So that gives us this intermediate. With sufficient base, we can remove the other alpha hydrogen, which would once again attack this carbon here with the leaving group, and as shown in this example. And that leads to closing of the ring. So in this example, we started with an alkyl halide that had 4 carbons. Those 4 carbons are shown here, and they're both, at least the 2 ends of the dihalide are attached to the same alpha carbon, since the deprotonation occurred there twice. And then that enolate that was made in each case attacked a carbon with a leaving group, so the top one, and then later the bottom one. And so we ended up making a ring that is 5 carbons long and centered around the alpha carbon in between the 2 carbonyls. If we add aqueous acid and heat it up, we can hydrolyze these esters into a carboxylic acid. And then since they're beta to each other, one of these carboxylic acids that would result would be eliminated through CO2 or through a decarboxylation reaction. So that will leave a single carboxylic acid as shown in this product here. Notice the carboxylic acid is attached to the cyclopentane that we have here. So this carbon here is this carbon, and then let's say if we kept this ester and then eventually turn it into carboxylic acid, this carbon would be this one highlighted here. Now note that we don't necessarily have to do this second step. We could stop the reaction if we wanted to at this step. We are essentially combining a double alkylation reaction followed by a decarboxylation reaction to make this carboxylic acid, but we don't necessarily have to do that. The decarboxylation reactions of beta carbonyl carboxylic acids is actually an important biological reaction that occurs in a few places. One of those places is the citric acid cycle in step 3 of the citric acid cycle. So that refers to going from isocitrate to this alpha keto glutarate. Notice that we have highlighted here in green carboxylate, which is the conjugate base of a carboxylic acid, and that carboxylate is beta to this alcohol. So they're on adjacent. We have a carboxylic acid, we have a carbon in between, and then we have that carbon with the alcohol. In this step, NAD+, which is a oxidant that cells have available, will oxidize that alcohol into the ketone that we see here in the product. And once that ketone is formed, it's going to be beta to the carboxylic acid we had there. And so this molecule will undergo a decarboxylation right after the oxidation of that alcohol. So that is the reason why in the product we only see a hydrogen there, since the carboxylic acid is completely removed. In this question, we're going to try to use the malonic ester synthesis to prepare the following compound, which is shown here. Note that this is a carboxylic acid attached to this carbon, which has a methyl group to the right, and it has, it looks like 1, 2, 3, 4, an isobutyl chain to the left. Now, in this reaction, the question asks us to use the malonic ester synthesis to prepare the following compound. You do not need to know, at least for this class, what exactly is the malonic ester synthesis, but you should be able to use alkylation reactions combined with decarboxylation reactions to form a carboxylic acid that has certain alkyl groups on it. In the malonic ester synthesis, we generally start with a diester, such as this one, and we can use base to form an enolate of the alpha carbon. So notice these two esters are bound to this center carbon. So it looks something like this. It starts off with a carbon in the middle, and then there's an ester on the left. There's an ester in this direction. And it doesn't matter which alkyl groups are on the ester. So we're using here an ethyl group on both esters, but it doesn't really matter which ones we have. And then we're going to use base to form an enolate from the center carbon, and then we could add alkyl groups from the corresponding alkyl halides. So if we're trying to make this particular carboxylic acid, which is shown here in the skeletal structure, this is what the question asks. We just converted it to a skeletal structure. Thinking about this reaction backwards, we want to have diester. So here's a carboxylic acid that would come from an ester, and we would have another ester coming from that same carbon. And we could add this methyl group and this isobutyl group through alkylation reactions with the appropriate alkyl halides. Then if we do a decarboxylation, we can remove one of the ester groups and the other one gets turned into a carboxylic acid. So that's essentially the strategy we use. So to add a methyl group or an isobutyl group, we need the appropriate alkyl halide. It doesn't matter which one you add first. We can add the isobutyl group first. So if we add sodium methoxide and then this alkyl halide, we can add the isobutyl group attached to that center carbon, which is this one here. And if we repeat the reaction with sodium methoxide and methyl bromide, we can add now the methyl group. So that would be this methyl group here. The isobutyl group is this one here, which we already added. If we add aqueous acid and heat it, we can hydrolyze these two esters. So there's two of them shown here in parentheses. We would be converting them to carboxylic acids, and one of them would be eliminated. So at the end, we end up with a single carboxylic acid, which is attached to a carbon, which is the alpha carbon, this one, with a methyl group and an isobutyl group. Review some of the reactions from this chapter. In the first reaction, a ketone is treated with acetic acid and one equivalent of iodine. In the second reaction, an alpha bromo ketone is treated with pyridine, which is a base, and heated. In the third reaction, symmetrical ketone reacts with excess chlorine and excess sodium hydroxide. In the fourth reaction, a ketone reacts with excess bromine, excess sodium hydroxide, and aqueous acid in the second step. Notice this is a methyl ketone. In the fifth and last reaction on the slide, unsymmetrical ketone reacts with LDA and an alkylating agent. In this first question, we have an unsymmetrical ketone and we're reacting with iodine, one equivalent, and acetic acid. So this will be an acid catalyzed alpha halogenation. This reaction generally will add an iodide or some other halogen to the more substituted side of the ketone. As long as that more substituted side has an alpha hydrogen, we can do this. So in this example, the left side here, the iodine should end up there by forming an enol that forms between the two carbons here, the carbon on the more substituted alpha carbon and the carbonyl carbon. And so for that reason, we have this as a product. When we add pyridine, which is a base, and heat an alpha halogenated ketone, we would do an elimination reaction. So we should get a double bond by removing the halogen and a hydrogen on the beta carbon. So in this example, we could remove a hydrogen from this carbon or this carbon. Either way, we're going to get the same product since it's going to be a symmetrical product. We have an excess of chlorine and excess of base. So this would be a base promoted alpha halogenation. So every alpha hydrogen of this ketone will be substituted with a chlorine. So for that reason, we get this as a product. In the next reaction, this is pretty much the same reaction as reaction C, except that we're using a methyl ketone, so there's a twist at the end. So after replacing all of the alpha hydrogens on this methyl group with bromine, the sodium hydroxide will do a substitution reaction through this carbonyl and eliminate the carbon with the three bromines on it, so you end up with a carboxylic acid. Note that the second step is acidic or aqueous acid, so for that reason we get the aqueous acid as opposed to the conjugate base of the aqueous acid. Adding LDA to an unsymmetrical ketone will lead to deprotonation of the least substituted alpha hydrogen, so that would be the hydrogen on this carbon, and then that forms an enolate there, which can attack this alkylating agent, so attack the carbon with the leaving group, the tosylate, and you add a benzyl group, which is a CH2 to a benzene ring. Here's a few more reactions for this chapter. So we start off with a beta keto ester, and we're going to add LDA and methyl bromide. In the next reaction, we're going to use an unsymmetrical ketone, add LDA at low temperatures, and then TMS chloride. In this third reaction, we're going to use a silo-protected enol, react it with TBAF, followed by aqueous acid. And then lastly, we're going to have this beta keto ester, and we're going to add sulfuric acid, water, and heat it up. When you have a 1,3-dicarbonyl such as this, and you add base like LDA, you will remove the hydrogen that is in between the two carbonyls. That's the most acidic hydrogen. You form an enolate there. That enolate will react with an alkyl halide to add an alkyl group at that position. So methyl bromide will lead to adding a methyl group there. In the next example, we have an unsymmetrical ketone. By adding LDA at low temperatures, we will form the kinetic enolate. So one way of looking at this is LDA will remove this hydrogen. That enolate that forms has two resonance forms. So we can move that negative charge towards the oxygen and form this enolate that is sort of shown here trapped with the silicon protecting group. So that oxygen will react with TMS and attach the TMS group. Remember, TMS is short for trimethyl silo. So it's a silicon attached to the oxygen with 3 methyl groups. In the next step, TBAF, which is a fluoride source, will remove the silicon protecting group, exposing the enolate, and then that enolate will be protonated to become a ketone. There's two ways to look at it. When you protonate this enolate, you get an enol, and enols are always in equilibrium with the carbonyl. Another way of looking at it is this: once you expose the enolate, we can form the other resonance form, which would be moving the negative charge to this carbon and moving the double bond between the carbon and oxygen. And then that negative charge on this carbon will be protonated by aqueous acid, giving you the ketone. In the last step, when we add sulfuric acid and water, the first thing that's going to happen is this ester will become a carboxylic acid. And by having that carboxylic acid with a beta carbonyl next to it, it's going to decarboxylate. So in other words, you're going to remove this group here entirely, and you end up with a ketone. In this synthesis problem, we'll need to convert a 1,3-diester, which by the way is diethylmalonate, into an amide that has a cyclohexyl group at the alpha position. Looking at the reactant versus products, one of the things we have to recognize is that esters are interchangeable with other acid derivatives. As we learned in the ethyl substitution, you can take different acid derivatives and convert them into each other. So we can presumably convert one of these esters into an amide. As far as adding the cyclohexyl group, one of the ways we can do that we learn in this chapter is by doing an alkylation of the alpha position. So that would be this one here, with a dihalide, an alkyl dihalide, that would allow us to essentially do two substitution reactions with the halogens to add the two sides of the dihalide alkyl group. The other ester can be removed, as we learn in this chapter, by first hydrolyzing the ester into a carboxylic acid and then doing a decarboxylation. So the way we would answer this problem could be that we add base to deprotonate this position, and then add a dihalide so that we could add the cyclohexyl group. So notice the cyclohexyl group has 1, 2, 3, 4, 5 carbons,
The 6th carbon is actually the alpha carbon. So we need to have a dihalide that has 1, 2, 3, 4, 5 carbons, 2 halogens on each end. And then if we add an excess of this base, we should be able to cyclize that chain by forming the enolate first, which would attack one of these carbons, do a substitution, eliminate this leaving group. And then if we add enough base, the reaction can repeat. So the second alpha hydrogen can be removed, which would then attack the other end. So this carbon chain is already attached by the first reaction. So we can now attach this side and cyclize that ring. Now we have this as a product. And if we add sulfuric acid, water, and heat, we can hydrolyze the two esters into carboxylic acids. Since the carboxylic acids are 1,3 to each other, in this reaction, when we're heating, we're going to decarboxylate one of them. And so for that reason, you see the product here with only a single carboxylic acid. The other carboxylic acid, which used to be on the right side here, will be eliminated as a CO2 molecule. Last step is taking this carboxylic acid and doing an acyl substitution with the appropriate amine. So if we want to add a nitrogen with an ethyl group, we have to add this primary amine with an ethyl group. Adding DCC will make the reaction easier, so we can do the reaction at room temperature. And so that will convert the carboxylic acid into the amide, that you see in the product.